Welcome to Brain Vision.
In this problem, we have an amusement park ride which consists of a car and a passenger and cable. This ride travels along a circular path with a given radius, and we want to calculate the speed of the car after a given time, provided that the cable is pulling at it at a given rate. So we'll first apply the conservation of angular momentum. And we know that at t is equal to 4 seconds, the radius r, which we'll call r2 after the 4 seconds has elapsed, is the initial radius 8 minus 0.5 times 4. And this is 6 meters. So r after 4 seconds is now 6 meters. And we use this and apply the conservation of angular momentum as follows. The angular momentum of the system about 0.0 at t is equal to 0 seconds must equal to the angular momentum about O after 4 seconds. So this is R1 times the mass of the ride, m times V1, must equal to R2 m V2. But remember, this is the tangential component of the velocity that we are given for V1. So the radius, or the distance to point O, is 8 meters, and that's multiplied by a mass of 200 kilograms times V1 is 3 meters per second tangentially. And this must equal to a radius of 6 meters after a time of 4 seconds like we calculated, multiplied by the mass of 200 kgs, but we don't know the final tangential velocity v2t. Now, if you rearrange this equation, we can find this velocity, v2 tangential, as 4 meters per second. There's only one unknown in that equation. So we have the tangential component, and we are given the radial component to be 0.5 meters per second. And so therefore we can find the resultant speed of the ride v2, and this is simply the square root of the tangential component of the velocity squared plus the radial component of this final velocity squared. And so that's the square root of 4 squared plus 0.5 squared. And so we get the speed of the passenger and ride after 4 seconds to be 4.031 meters per second. Or if we keep our significant figures, that's 4.03 meters per second. Now, to calculate the work that the cable does, we'll apply the principle of work and kinetic energy. And from here, we know that initially we have kinetic energy T1 and the work done. So if we add the work done by the cable as we go from t is equal to 0 to t is equal to 4 seconds, then we have a new kinetic energy after 4 seconds, T2. So the initial kinetic energy of the ride is a half mv squared. So half times 200 times the initial speed, which is 3, and that's squared, plus the work done by the cable as the ride is moving, which we wish to solve for, u, and that's equal to a half times m times the final velocity, 4.031, and that's squared. So as we can see, we can rearrange here and find the work done between 0 and 4 seconds on the cable on the ride is 725 joules.